In this video, we're going to learn about the first derivative test for local maxima and minima. My goal is that this video will help you learn how to use the first derivative of a function to determine whether each critical point of a function is a local maximum, a local minimum, or neither. And I hope also that this video will illustrate how a critical point could be neither a local maximum nor a local minimum. So here's the question of interest. Suppose we're given a function f, like maybe we have a formula for f, and we know the locations of the critical points of that function. Just keep in mind critical points are points where the derivative of f is 0 or undefined. The question is, how do we determine whether each of those critical points is a local maximum, a local minimum, or neither? Previously, we saw that a function has a local maximum at x equals p if the function value at x equals p is the greatest value that the function has near x equals p. And similarly, a function has a local minimum at x equals p if the function's value at p is the lowest value that the function has near x equals p. But what about the case of neither? What does that look like? Well, a critical point is any point where a function's derivative is 0 or undefined. We see that this local maximum in this picture occurs at a critical point because the derivative at that point is 0, and the same is true of the local minimum we see here. But it is possible for a function to have a critical point, that is a point where the derivative is 0 or undefined, and not have a local maximum or minimum. An example would look like this. Have a function that sort of stalls out here, has a derivative of 0, but that point is neither a local maximum nor a local minimum. The example we're going to address in this video is the function x squared plus 4x plus 7. We're going to find out what the critical points are for this function and then classify those critical points as local maxima, minima, or neither. So first, just to find the critical points, we find the derivative of f prime of x, that is 2x plus 4. And then we find out where that is equal to 0 or undefined. The derivative is always defined because it's just a linear function. So we want to find out where the derivative is equal to 0. That'll occur when 2x plus 4 is 0, or x equals -2. But to figure out what kind of critical point this is, we're going to have to think about what the shape of this graph looks like around that critical point. Does the shape look like this, where we have a graph that is rising and then falling? Or do we have a shape like this, where the graph is falling and then rising? Or do we have a different shape, where the graph is rising and then stalls out and continues to rise, or falls and stalls out and then continues to fall? We now know that one way of keeping track of rises and falls in a graph is to keep track of the sign, positive or negative, of the first derivative of the function. We know that when the first derivative is positive, the graph will rise, and when the first derivative is negative, the graph will fall. And that is the idea of the first derivative test for critical points. This is the first derivative test for local maxima and minima. And as you can see here, it gives a set of rules that helps us determine whether a certain critical point is a local maximum or a local minimum. These rules are stated in terms of the sign of the first derivative of the function. They talk about whether f prime changes from negative to positive or from positive to negative. But we can also think about these rules in terms of the corresponding behavior of the function f itself. So for example, if f prime changes from negative to positive, then that means that f changes from decreasing to increasing. And we know that if f goes from decreasing to increasing, then its shape is going to look something like this. And that means that our critical point is going to be a local minimum, which is exactly what this rule says. And the other rule says if f prime changes from positive to negative, but we can think about that as f changing from increasing to decreasing. And in that case, f is going to have a shape kind of like this, and its critical point will be a local maximum. So if you have a hard time remembering the rules for what f prime is doing and what those mean in terms of local maximum and minimum, you can translate those rules into statements about the behavior of the function itself, decreasing and increasing, or increasing to decreasing. These translations are nicely summarized in this. This picture shows an example of a local maximum and a local minimum, and shows the behavior of the function near the critical point for each one. Again, we have decreasing and then increasing for a local minimum, increasing and then decreasing for a local maximum. Now let's use the first derivative test to determine what kind of critical point f of x has in our example from earlier. We already determined that f has a critical point at x equals -2, and it's the only critical point. But what type of critical point is it? Is it a local maximum, a local minimum, or neither? To figure that out, we're going to use the first derivative test. We're going to analyze the behavior of f prime, positive or negative, on each side of x equals -2. To do that, I'm going to use a strategy, which is to draw a number line, mark the point x equals -2, which is our critical point, and then test a point on each side of x equals -2. So I'm going to test the points x equals -3 and x equals -1. There's nothing particularly special about those points, except that there's one point on each side of x equals -2, and they make good test points because the inputs are integers. So let's now find the value of f prime at each of these points. F prime at -1 is 2 times -1 plus 4, which is equal to 2, and that's greater than 0. So we see that on the right side of x equals -2, f prime is greater than 0. And on the left side, we have f prime at -3 equals 2 times -3 plus 4. That's equal to -2, which is less than 0. So on the left side of x equals -2, we have f prime negative. F prime is less than 0. What does this tell us about f? This tells us that f on the left side is decreasing, and on the right side, f is increasing. And if f goes from decreasing to increasing, then we expect that f is going to have a local minimum at x equals -2. We can verify that by drawing the actual graph of f. There it is. And we see that we have a parabola whose critical point is a local minimum. You might have anticipated that because we know that this is a quadratic function. Its leading coefficient is positive, so it should be a parabola facing upwards. We should expect a local minimum. So that's an example of how to use the first derivative test to determine whether a critical point is a local minimum or maximum. And even though we could have done that for this example, just using what we know about quadratic functions, the first derivative test works for even more complicated functions where we don't have quite as much prior knowledge about how we should expect the graph to behave.